Have you ever wondered what the code is that runs mathematics itself? I mean, what's the underlying program? Today, we're diving into ZFC set theory, which is basically the powerful and surprisingly controversial operating system for pretty much all of modern math. So, here's our game plan. We'll start with the crisis that made ZFC so necessary. Then, we'll unpack what it actually is, get into its most debated component, then talk about its ultimate limits, and finally, we'll look at what might be next. All right, let's get right into it. To really understand why ZFC is such a big deal, we have to rewind the clock to the turn of the 20th century. This was a time when the entire world of mathematics was, believe it or not, on the verge of a complete and total meltdown. I mean, just imagine that for a second. This was the terrifying question that mathematicians were suddenly facing. They were discovering that their simple, common-sense approach to sets, the basic building blocks of everything, could actually lead to paradoxes that made no sense at all. The very foundations were starting to crack. See, on one hand, you had what we call naive set theory. It was simple, it was intuitive, it's how you'd probably think about it. But that simplicity was its downfall. It led to these absurd self-contradictions, like the famous Russell's paradox, and that forced a move towards something much more careful, a formal, rigorous system built on solid rules or axioms, designed specifically to prevent these kinds of logical disasters. So out of that chaos, a solution started to emerge. Mathematicians knew they had to build something new, a robust framework that could put everything back on solid ground. And that solution is what we now call ZFC. Now, the name sounds kind of technical, but it's just an acronym for its two key parts. You've got the Zermelo-Fraenkel axioms, the ZF, which are a bunch of very careful rules about what a set is. And then you've got the C, the powerful, and as we're about to see, super controversial axiom of choice. And this is why you should really think of ZFC not just as a dusty list of rules, but as the new operating system for modern mathematics. It's the base code. Almost everything you've ever learned in math, calculus, algebra, you name it, is like an application running on top of this fundamental ZFC system. Now, building this new OS wasn't easy, it was a huge effort. It really started with Zermelo's work in the early 1900s and took decades to solidify. The whole thing climaxed much later when mathematicians like Gödel and Cohen proved something really mind-bending about that axiom of choice. It was independent. You could take it or leave it, and the rest of the system wouldn't break. But here's the incredible irony. That C in ZFC, the axiom of choice, it wasn't just part of the solution. It created its own firestorm of controversy. It's wild, right? This one axiom, which was supposed to help fix things, actually became a primary driver of the foundational crisis itself. Its introduction created this deep philosophical divide, forcing everyone to argue over what it even means for something to exist in mathematics. So why all the drama? Well, because the axiom of choice is incredibly powerful. It lets you prove some really important stuff, but, and this is a big but, it does it by just asserting that something exists without giving you any way to actually find it or construct it. To a lot of mathematicians, that felt like magic, like cheating. And this debate raged for years. Okay, so just as mathematicians were kind of getting used to this new ZFC operating system, another intellectual bombshell dropped. And this one proved that the whole quest for a perfect, completely certain foundation for math was basically doomed from the start. Yeah, that bombshell came from a guy named Kurt Gödel. His famous incompleteness theorems showed that any formal system that's powerful enough to do interesting math, like ZFC, has inescapable limits. He proved that the dream of having one perfect system that could prove every true statement and prove its own perfection was simply impossible. Gödel delivered this 1-2 punch. First, he showed that in any system like ZFC, there will always be true statements that you can never, ever prove using the rules of that system. They're just true for no provable reason. And second, the system can never prove that it's internally consistent. We can't use ZFC to prove that ZFC won't one day lead to a contradiction. We just have to, well, have faith. So all of this brings us to a really fascinating place. If ZFC has these deep, fundamental limits, is it the end of the story? Is this really the final word on how math works? And the short answer is nope. While ZFC is without a doubt the dominant standard, it's the Windows or Mac OS of math, it is definitely not the only operating system out there.
People have come up with other powerful alternative ways to build the mathematical universe.
For example, you've got category theory, which is less about objects and more about the relationships, or arrows, between them. There's also type theory, which is hugely important in computer science and for writing provably correct code. And you even have things like fuzzy set theory, which throws out the black and white true-false idea and allows for things to be partially true.
What this all shows is that ZFC, for all its importance, wasn't the final chapter. It actually revealed that mathematics isn't some static set of ancient rules carved in stone. It's a living, breathing, dynamic field of inquiry where the biggest questions about truth and logic are still very much on the table.
And that leaves us with one last, really provocative question. Knowing that our main mathematical operating system has these built-in limits, well, that doesn't feel like a defeat. It feels like an invitation. It begs us to wonder what amazing paradigm-shifting discoveries are just waiting for us out there, right beyond those limits.